Everyone, and welcome to another CAS webinar. I hope by now you've had a chance to have a look at our newly created YouTube channel. If so, please like and subscribe. I will upload tonight's presentation to the channel sometime this week, so that those who cannot attend can have a listen to the presentation, and it also allows us to have another listen as well. There was, as you know, a change at the last minute to our speaker for this evening, and Julian, when asked, kindly agreed to step in at short notice. So, a very big thank you must go to Julian. The next meeting is on the 29th of June, when our very own Roy Bryce will give a presentation entitled The Geology of Mars. Tonight's presentation is entitled Heavy Metals, What Can They Tell Us? So let's give Dr. Julian Onions a warm CAS virtual welcome.
Oh, right. Good evening, everybody. And it's great to be back here again. Thank you all for turning up again. And I hope you're not too sick of me, at least. So tonight, as Alice Amanda said, we're going to be talking about heavy metals and what they can tell us. So it's in sort of two parts. One is what are metals and how they're made and what do they mean to an astronomer. And the second part is really about what they can tell us about the solar system, life, the universe, and everything, basically. So I hope you can all hear me okay, and this is coming through. I know the last time I tried this, I forgot to turn the microphone on, so let's hope that's not the case here. So, heavy metals, what can they tell us? So to start with, let's start with a few definitions. So metals, we'll consider what they are, and then go on and discuss how they are made, and then finally, what can they actually tell us about the universe, sort of thing, and what's going on out there, and what we can understand. So we're going to start with the periodic table, and periodic table, which anyone who's ever sat in a chemistry lecture or lecture theatre will know, from sort of staring at the walls, is a good place to start, because this sort of gives us a good definition of where things are. Although, so they're going to feature a few times through the talk, and they started very early with this guy Dobryna's, his triplets. So he noticed fairly early on that there was some, excuse me, some similarity between certain of the elements. So things like chlorine, bromine, and iodine all did very similar things, especially when you mix them into compounds, and they all had very similar things, reactions. Same with calcium, strontium, and barium there, and they also seem to go up in a sort of regular way. So this was kind of the predecessor somewhat to the periodic table. But of course, this really took off with Dmitri Mendeleev, and he came up with a much better periodic table, because he actually had the belief in his system that he could arrange the elements into some sort of order and some sort of classification, into columns and rows. And despite not having all the elements discovered at this point, he had the sort of belief that his system was probably going to be right, so he could predict that there were still gaps in the periodic table and things were going to be found. This wasn't entirely unexpected, because people were still finding new elements at this stage, and there was a sort of steady stream of new elements coming along. So that's Dmitri Mendeleev, and this was before his appearance in ZZ Top, obviously, because he fits right in there. So this is a sort of version of his periodic table, and you can see it looks, if anybody recognises the periodic table, it looks somewhat similar to today's periodic table, except there are some big gaps in it there. You can see these white spaces where he couldn't find anything to fit in those, but he thought there was probably something there because the jump between elements seemed too great, and the variation between their properties seemed too great. So he had the sort of foresight to put them in. And today we see the following. This is with these pink elements that were discovered since his time. And in fact, there's a whole new column there on the 0, or sometimes it's put on the extreme right, of the noble gases, because they don't react with anything. They were not so easily found in nature until certain experiments could find those out. So that's an interesting table. So you can see all the green ones are Mendeleev's, the pink ones are known since his day, and the ones with a sort of cross hatch are the Dobereiner's triads, as he classified them. So you can sort of see how that builds up. So today we have a periodic table like this, and this is sort of right up to date. We've got as far as element 118, which is down here. Let me just see if my pen works. Okay, so this is right down at the bottom. So from about here onwards, and in fact from here onwards, because this actually flows onto here, stops over here again. These are all what's called transuranic elements. These are all being made in labs because they are too short-lived to exist in nature, given the Earth is as old as it is. So they might well be made in the universe, but because they have a very short half-life and there are no stable versions of it, they are very, very rare on Earth, if you can find them at all. And more usually they're certainly made, especially when you get down to things like 118 ognesium, which is extremely transient. I think it has a half-life of a few milliseconds or something like that. So by the time you've made it, you've got just a few milliseconds to actually detect it before it falls apart into other elements. So as you get above 92, they get increasingly radioactive and harder to make. So it's not to say we won't go beyond 118, but the gains to be made are sort of just for the record books, really. Whatever you make, even up to 118, just falls apart almost as soon as you make it. So it's only a sort of intellectual exercise to go and make them. So what do we know about metals? Well, we know they're all hard. We know we make a lot of construction stuff out of them because they have these hard properties. They're also opaque. You can't see through them. They're generally very shiny because they have a lot of electrons floating around and reflect light. And they're also very good conductors, typically of both heat and electricity. Some better than others, but they, on the whole, they're pretty good conductors as compared to the non-metals. Now, chemists sort of lay it out like this. All those things in this sort of silvery colour are metals. The things in the sort of goldy colour are non-metals. And the ones in green are what I would call semi-metals, or it's called here metalloids, a term I hadn't actually heard until I found this drawing. So that's kind of how the chemists divide things up. And you can see, like 75–80% of the periodic table is classified as metals. So this is going to stand us in good stead when we get to the astronomers' periodic table and we see what that's got in it. However, you can get lots and lots of different periodic tables. I mean, here's an interesting one that has tried to squeeze things in. So you've got different rows of things there that have been squeezed around because the periodic table, although it is periodic, it sort of stretches quite a lot as you go down the table. Now, the trouble with this is if you get late at night preparing a talk like this and you start to Google periodic tables, you find there's actually quite a lot of periodic tables. And if you are ever stuck with insomnia or something, it's quite an interesting thing to do because you can find a lot of periodic tables. So here's an interesting one. This is the organic chemist's periodic table. So organic chemistry is all based around carbon. So you can see there, carbon is the star of the show, and basically everything else is displayed there in its relationship to carbon. So there's a whole load of catalysts there in the sort of bluey colour. There's boring things over to the left, lazy things over to the right, and then other stuff that he can make use of. But generally everything just hovers around carbon and sticking a few things onto carbon. So that's the organic chemist periodic table. Here's another one. This is quite a nice one, I thought. Elements and their country of discovery. So you can sort of see where the elements have come from. Quite a lot of them were known to the ancients, things that you get in sort of very pure forms like lead and gold and silver. But then, there's quite a few there from the UK that's been discovered. But increasingly, you can see the later ones are down to sort of Russia and the US. They're the only ones making these huge, heavy elements that really don't last very long. And as I said, it's more for the record books than anything else. So that's quite a fun periodic table that's got some sort of history to it. It's one that has no relevance whatsoever, really, to this talk, but I thought it was quite interesting because it does have a periodic table of metals, but these are metal bands. So you can see there all sorts of metal bands. And if we just zoom in onto one side of it, you can see there we have Led Zeppelin and Scorpions and Deep Purple and all sorts of other things. So it seems like once you get into a subject, people are sort of drawn towards the periodic table and putting things into the periodic table. So I don't know why they do it, but here's another one of classic rock this time. You can see Aerosmith and Van Halen and other things there that people have squeezed in. It's not a very scientific one because they're spread across lots of periods. But then there's some really weird ones. I mean, here's one about music notation. I mean, why would you want to put that into periods particularly, or group things together like that? But somebody's done that. Another one, grouping together irrational nonsense. So you see different things, based on divination and psi abilities, alternative medicine, and all sorts of things like that, all grouped into different periods. So you see, I do like the quack block and the credulous block of elements, but quite why they do this. Now this one is quite bizarre. Periodic chart of business lawyers. I mean, this is just taking things to extreme. I don't quite know why you would do this, but somebody did it. Somebody took the time to sit down and make a table of periodic business lawyers. So there you go. That's a rat's nest of Wikipedia and Google links that you can fall down if you're stuck late at night Googling periodic tables. So anyway, where were we? Yes, let's get back to metals and heavy metals and get to some astronomy. Now, the astronomers' periodic table, as you may know, is really, really simple. They have hydrogen, helium, and metals. Everything else is metals. They really don't consider anything else apart from that. And as we saw early on from the chemist's periodic table, it's not a bad approximation. 75 to 80% of the elements in the periodic table are metals. So sweeping the other 20% or something under the rug and labeling them as metals isn't that bad. But anyway, this is where we get to. Astronomers, whenever they talk about metals, they refer to anything heavier than helium, basically. So any element that isn't hydrogen or helium. Now, another nomenclature or naming scheme they use is also X, Y, and Z. So you will often see the metals in a star, which means anything that isn't hydrogen and helium, referred to as their Z value, and it's a capital Z, which is unfortunate because it looks exactly the same as a small case Z. But this comes from just sort of labeling the quantities. So if you were looking at a typical star, X would be the amount of hydrogen, Y would be the amount of helium, and Z would be the amount of everything else. And that's what we call metals. So sometimes you see it as a Z value. I say it's not a great symbol you can see why it's come about from X, Y, and Z. But Z is also an abbreviation for redshift, although it's a lowercase z there, but because you often can't tell capital Z to lowercase z if you're just looking quickly, it is subject to some confusion. Now, is this well found? We have to say yes, it probably pretty well is. So this is what the universe started with. 74.6% hydrogen, 25.4% helium, and the rest tiny bit of lithium and perhaps a little bit of something else, but by and large nothing else really. So to a good approximation, the universe started off as 75% hydrogen, 25% helium, and that's the way it stayed for a long time. Oh, if we look now, the universe is a bit more evolved now, and we now have 2% of other stuff. So besides hydrogen and helium, we now have some other stuff, broadly labelled metals, which we know are everything else. If you want to know how much is in the sun, we're about 2%. So we have 2% impurities in the sun. So the sun is by and large hydrogen and helium, and the 2% left over is metals. And you can reflect on that, given that our solar system is made out of the same material as the sun by and large. All the hydrogen and helium, certainly for the rocky planets, has more or less disappeared to a good extent. So we are, the Earth, Venus, Mars, Mercury, they're all made from this 2% of metals that are left over. But if we look on the Earth, there is very little of metals, the non-metals rather, hydrogen and helium. There is almost no helium on the Earth. What hydrogen there is tends to be locked up in other elements, such as water and other compounds like that. And so, by and large, we are made of metals on the Earth. And just for completeness, this is how much of the things we have on the Earth. So this is a good pub quiz question. What's the most common element on Earth? And it's actually oxygen, which you might not think of if you just sort of think what's around you. There isn't that much in the air, but there's an awful lot locked up in the crust. So a lot of the crust of the Earth is silicon dioxide, which is sand. So there's 2 parts of oxygen to 1 part of silicon for that, and magnesium oxide and water and so on. All have got oxygen because it's a very reactive element. It tends to combine with lots of other things. Aluminium oxide and iron oxide are also very common. So you can see there roughly what it is. It's almost no helium because it's a very light gas. It doesn't form any compounds, so it tends to what helium does occur on the Earth tends to be given off as radioactive decay deep underground, and it sort of bubbles up to the surface. Once it's free of the surface, it goes into the atmosphere and then straight up, much like a helium balloon, straight to the outer atmosphere, and then gets blown off into space. So there's very little helium apart from that coming from radioactive rocks. That's making a reasonable supply. So, where does it all come from? Where does all these elements and things that we call metals, where are they produced? And before that, we're going to have to do a little bit of nuclear physics, just so that we're all talking the same scheme. I know some of you probably know some of this stuff, but I thought I'd make sure we're all on the same page. So we're going to start with atoms. As it says there, don't trust them because they make everything up. So on the left-hand side, this is a hydrogen atom. Get my thing. So this is a hydrogen over here, and this is the simplest form of hydrogen. It has a nucleus here, and this blue bit, which is actually a proton, if you want all the names, and an electron going around it. So that's the very, very simplest atom you can get. Hydrogen with an electron going around it. And this is a simplified picture because the electron doesn't actually do that as such, but it's a good approximation. Excuse me. When you get on to more complicated elements, then over here we have something with 4 protons in it, 4 neutrons. So protons are what give the nucleus its type, and the neutrons, I'll talk about it a little time, but you typically get as many electrons around as you get protons in the nucleus. But to go into a little more detail there, we start with the nuclei. So the proton is what gives the element its flavour, what gives it its characteristic. So the number of protons, it gives you the atomic number. So hydrogen has atomic number 1, it has 1 proton. Helium has atomic number 2, so it would have 2 protons. Lithium 3 protons, and so on. So you could work all your way up to element 92 uranium, which would have 92 protons in it. So that's kind of how we name them. The problem with protons is that they are positively charged. They have a positive charge, and 2 charges of the same sign, so 2 positives or 2 negatives, if you try and push them together, they repel each other quite strongly. So it's quite difficult to make nuclei out of these things. So if you go to helium, you want 2 protons together to make helium, and that's a problem because the 2 protons want to repel each other. They don't like being together. So we have this other particle called the neutron, and this has no charge. So if you put this in a nucleus, it doesn't make any difference to the element type. So you can stack them into a nucleus up to some sort of limit. But the thing they bring to the party is they have a sort of stickiness. So if you put them into the nucleus, they help to stick together these positive protons that would otherwise just fly apart. So with that's your basic introduction to nuclear physics. And we can build all these elements here. So these are the first 4 elements: hydrogen, helium, lithium, and beryllium. And as you can see there, they all have the requisite number of protons. So that gives them the atomic number: 1 for hydrogen, 2 for helium, 3 for lithium, 4 for beryllium. But as I've already said, helium will not stick together. The positive charge on those 2 protons in helium is too strong for the nucleus to stick together. So you have to add something else into the mix. So typically there is at least 1 neutron in there, and as I have sometimes called these sort of nuclear Velcro. They have a sort of stickiness to them. So that lets the helium stick together with one of these neutrons, sort of helping to glue these 2 protons that really don't want to be next to each other. It helps to glue them together. So that's helium 3, so-called because there are 3 nucleons in it. So it has an atomic number of 2 for the 2 protons, but an atomic weight of 3 because there are 3 things in the nucleus. Helium 3 isn't very common. In fact, it's pretty rare on Earth. You can get hold of it, but it costs quite a lot compared to helium 4, which we tend to throw around a lot in party balloons and weather balloons and other things. So helium 4, which has a second neutron in it, that is much more common. That's the more common version, and that is a very, very stable particle and is often emitted in radioactive decay because it's a sort of very stable thing to stick together. As you see, there's 2 sticky neutrons to keep the 2 protons together. So as we go up, it just gets more of the same. Lithium has at least 3 neutrons to stick it together. You can get variants with others, but they tend to be very radioactive. And similarly up to beryllium, I put it there with 4, but we'll see that's a bit of an issue. There is a version of beryllium 8, but it's actually very unstable. So now you know about basic nuclear physics, what goes on in the nucleus, or at least you do if you haven't dropped off. Oh, I've got a spelling mistake there. The Big Bang. I don't know what that is. It should be the Big Bang. So this was the very first event, happened 13.8 billion years ago, and very soon after that, in fact about a second after it, everything condensed out of the Big Bang, and we got lots of these neutrons and protons flying around all over the case, all over the universe, which wasn't very big at that point, and they can collide together, and for a little while they can actually go through all these reactions that you can see here, and they can produce up to these other elements. So you can see all sorts of strange reactions there. But you can see mostly it's hydrogen to different versions of hydrogen, hydrogen to helium, or hydrogen and helium to lithium. And there is a bit of beryllium in reaction 10. But you can see also reaction 12 takes beryllium 7 and it sort of decays down to lithium. So this is what goes on very soon after the Big Bang, and it only happens for 17 minutes. It happens 3 minutes after the Big Bang to 20 minutes after it, and it goes through all these reactions. But the sort of reactions 1 to 10, 1 to 9 probably, are the most favoured reactions that happen in there. So that's why we get all this hydrogen, which is what we start off with, helium, and a little bit of lithium. So it goes through all those reactions, and that's about as far as we can go before the universe gets too cold and shuts off those reactions. There's also a lot of radiation around there, so it tends to break things apart again. So as I said, this occurs very soon. So this is the timeline of the Big Bang. So this is the Big Bang over here, starting here. Then we go across here. And about 1 second, we start to get protons and neutrons condense out of the Big Bang, which was extremely hot. And then at about 1 minute, we get this nucleosynthesis where we get hydrogen and helium being made and a little bit of lithium. And then at 20 minutes, it all shuts off again and nothing further happens for millions of years. So that's why we end up with this picture here that we get helium, hydrogen, and just a tiny fraction of lithium. So where does all the other stuff come from? Where does the oxygen that I'm breathing, the carbon that makes up my body, the phosphorus, the aluminium, steel, all those things, where does all that come from? And Carl Sagan said it rather poetically, saying that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were all made in the interiors of collapsing stars. We are indeed made of star stuff. That's Carl Sagan. Now that's sort of 90% correct. And we'll just correct him a little bit as we go along. But it's a good approximation to everything. A second way of putting it, I heard Jim Al-Khalili say, is that no, we're actually all made from nuclear waste. We're all the waste products of stars. So you can think of yourself as nuclear waste if you're feeling less poetic, or even less poetic. Chris Impey, I've heard another astronomer at Arizona, says we are all star bath. We're all the ejector of stars. So let's go about discovering how these elements are made. First thing to do is, how do we actually know where these elements are, and how can we actually go about finding where elements are? So we need to do a bit of metal detecting. So we need to work out how to work out which metals are where. And we're helped a lot with this by the advent of spectroscopy. Now this comes from, so this is the nucleus here of an atom. That's the bit with the neutrons and protons in. And these rings around here are where the electrons live. Now this diagram is not to scale. If you managed to blow an atom up very, very large so you could actually see it. In fact, you made the nucleus the size of a marble, so about that sort of size, and put it on the centre spot of a football pitch, the electron would be going around in the stands, so floating around amongst all the spectators, if they were indeed allowed out to watch a football match. But due to the laws of quantum mechanics, an electron can't go anywhere. It's only allowed into certain places. These are the orbits around the nucleus. So in this case, it can go into this orbit here, which we give orbit number 1. I'm not very good at writing this. That should be a 2. This should be a number 3. So there are 3 orbits here shown, but there's actually almost an infinite number of them, but they get closer and closer as you work them out. And electrons can only go in those particular orbits. Now they can jump between them almost instantaneously, and when they do, they lose energy. So here we're showing an electron jumping from shell 2 down to shell 1, or orbit 2 down to orbit 1. And when it does, it has to give out amount of energy to lose that amount of energy that would have kept it in orbit 2 to descend to orbit 1. It's a bit like sort of going down a mountain, but more like going down in a cable car. You can only get off at certain stops. You can't just stop anywhere you like on the mountain. You have to go down in stages. But there is a certain energy between these two, and when it drops down that far, it gives off the energy as light, and it always appears as the same wavelength. And the wavelength will be exactly the energy that is the difference between these two orbits. So you can see from this simple diagram, you can actually give off 3 types of light. You can give this one, you can give this one, or you can give this one. This would be the most energetic because it's losing the most energy. This would be the second energetic, and that's the third. And each element has these different shells, and they're very different for each element. So hydrogen has a particular ring of electrons. Helium has a different rings. So it has orbits, and it has a orbit 1 and orbit 2 and orbit 3, but they're different levels. So it's like having different cable car stops for each of the atoms. But this is extremely handy because we can look at the light signature of almost anything, and if we see certain lines in it given off by these elements, then we know exactly what they are. And here we have another periodic table. I said there's going to be lots of periodic tables, and this is the visible light from each of these elements. This is what you would see if you heat one of these elements hot enough so that it sort of glows with the characteristic light. And you can see over here we have hydrogen with sort of these 3, including this one here is a very prominent one, hydrogen alpha. But you can see here helium, with the next one up, has a different set of lines. You know, it has a light yellow one, which hydrogen doesn't have. And over the years, chemists and physicists have worked out exactly where those lines are. We know exactly what frequency those lines are. So if we find something with a particular line, we know exactly what that element is. And you can see there you have all sorts of interesting lines there. And you can separate out the elements quite easily just by passing them through a spectroscope. So that's how we work out what's actually in stars, and gives us some guidance that what follows is true. Now we get to the actual real story. Where do they all come from? And there's 4 ways that elements get made after the Big Bang. First one is nuclear burning. Then there are 2 processes, the S and the R process. And finally, there's cosmic ray activity. So let's go through each of those in turn and discuss them. So the first one is nuclear burning, and this is what happens in all stars. All stars that are shining in the night sky, as long as they're still active, are doing nuclear burning. Now this is what our sun does. So our sun is busy at the moment converting hydrogen into helium, and it follows this mechanism. So you can see it's slightly more complicated than just getting 4 hydrogen atoms together and making it into a helium. There are a few steps amongst them. And in particular, this first step, where you, at the very top, where you can see 2 hydrogens coming together, this one here, this is the hardest step to occur because these 2 hydrogens are strongly repelling each other. They're like 2 poles of a magnet. And in fact, that gives me a chance to use this animation I did. Well, it's a video of what I did on my kitchen table a few years ago, and I did this by sliding 2 magnets across the table, and there's a bit of Velcro on each of them. You can perhaps just see the black fuzzy stuff on the edge, but I'm trying to slide the 2 poles of the magnet together, and of course they're going to repel each other as they come together. But if you can get them going just fast enough, then you can overcome that magnetic force, and you can get them to actually touch, and the Velcro will hold. So that's exactly what we're trying to do in the fusion. You're trying to overcome this 2 positives of a proton enough that the 2 can stick together. If you do it too fast, then they sort of bounce off each other. So it's got to be just sort of right to get it right. And hopefully you can see this as I slide them across the table. Most of the time they just miss each other, or go sliding off. But once in a while they do get to stick together. So I thought that was a good example of what's going on in the sun. That this very first reaction of trying to get two hydrogens to stick together, you've got to get it hot enough that these hydrogens are going fast enough to actually bump into each other, get close enough, despite the positive force between them. And it's also got to be dense enough so that they're not all the time missing. They've got to have a reasonable chance of colliding, or at least be on a collision course to get through that. So that's what happens in the sun, and this is the overall time scale. And you can see this first reaction is really slow. So here we have the first reaction, 10 to the 9 years. That's a billion years. So for any two protons to come together and stick, it's about one. It takes about a billion years for that to actually happen. So this is the limiting rate reaction of the sun. This is what stops the sun exploding like a bomb or something like that, because this reaction runs so slowly that this is basically what slows the sun down from using up all its fuel. Otherwise, the sun would all, gone through all its fuel by now, much quicker than that. But you can see once you're past that reaction, it's much quicker. So the next reaction just takes around a second or two to actually occur there. And the third reaction to make helium, it's a million years, but that is so much quicker. It's 1,000 times quicker than this first reaction. So that's kind of interesting. That's why the sun lasts as long as it does, because it can't go through this reaction very quickly. And it's also why on Earth, if we're trying to do nuclear fusion on Earth, we tend to try and work from this, which is heavy hydrogen. So that's a proton with a neutron. The neutron isn't actually helping anything here. It's not helping the hydrogen to stick to itself, because it's all on its own. But it's quite happy to just go along for the ride. So you can get heavy hydrogen, and you can make heavy water, in fact, with heavy hydrogen. And there is a certain amount of heavy hydrogen in seawater. So this is a much better place to start from if you're going to do nuclear fusion on Earth, because this is a much easier reaction to start with, rather than this one over here, which is sort of the pure fusion process. There is another reaction in the sun and also bigger stars called the CNO, for carbon, nitrogen, oxygen cycle. That's a little more involved. It's also a little more efficient, but it needs a great deal more heat. It needs about 15 million degrees to actually start this, and it gets progressively better the hotter you get. Our sun is about 15 million degrees, so it just about gets going with this. But when you get to much bigger stars, they can motor through this. But you can see you do need carbon, nitrogen, and oxygen here, which see if you're starting from scratch in the Big Bang, you don't have any of that. So this is what happens in the sun. In most simple stars, they are burning hydrogen into helium. So you get a mixture of hydrogen and helium throughout the sun, but it's only the hydrogen that takes part in the reaction. You get the two hydrogens that bang together and make a helium eventually. And then that just sits there because it's not hot enough to burn helium in the sun. So it just goes through burning as much hydrogen as it can get its hands on. And it's got to sort of move it around the sun to be very efficient, to drag down hydrogen from the outer layers if it wants to burn it all. But in many cases, the stars don't get to burn all the hydrogen they have, because they can't get it down to the center where the reactions are in time. And you probably know that a star is in balance between the gravity trying to squash it down and the nuclear explosions in the center trying to boost it out. But as it gets towards old age, it gets this big core of inert helium at the center that it can't do anything with, and it ends up just burning hydrogen in a sort of shell outside that. And the hydrogen burning gets further and further out and gets slower and slower as it moves out. Now, if the star is big enough, it can start to try and burn the helium. And the simple process to burn helium, if it could do it, would be this process. You take two heliums and bump them together, and you could make beryllium-8. So you've got two helium-4s, each with 4 nucleons, 2 protons in each. You make beryllium-8, which has 4 protons, so beryllium is element number 4, but atomic weight number 8 because it's got 8 things in the nucleus. However, this doesn't work because beryllium is extremely unstable, or at least beryllium-8 is. So as fast as you make this, it tends to fall apart. So this isn't a particularly good thing to do because you end up not getting any energy out of the reaction. However, there is a trick you can play, and this is why it's called the triple alpha, because these are called alpha particles, helium nuclei, is that if you can get another helium involved quickly enough, so you get the 2 heliums to come together to form a beryllium-8, which is going to fall apart in a few milliseconds. But if you can hit it with another helium very quickly within those few milliseconds, then you can jump all the way up to carbon. So you've gone 4, 8, 12. You've gone up in jumps of 4 basically, and groups of 2 for the atomic number. So you've gone 2 to 4 to 8, 2 to 4 to 6, sorry, for carbon. Carbon is atomic number 6 and atomic weight 12 because it's got 12 in the nucleus. So this needs a considerable amount of heat, much hotter than the sun currently burning. So it's got to collapse down and get very, very hot to actually trigger this. And we think the sun will get as far as this, but then it won't get very much further. But much bigger stars can do this process over and over again. So they can start to burn carbon, they can actually add another helium on to make oxygen, and then they can go through a whole sequence of reactions. And you can actually get this whole layering of burning. So in a really big star, you can get all these things happening. So hydrogen to helium on the outermost layers, and then a bit further in, where it's much hotter, you can get helium to carbon and oxygen. A bit lower down, you can get carbon burning to neon and magnesium, oxygen to silicon and sulfur, and then silicon sulfur to iron. And that's where it stops. You can't burn iron in a star. Iron you get no energy out of if you try and burn, so it's pointless trying. It actually uses energy up. And this all comes from this graph here, which you don't need to understand particularly. But along the bottom, this is going up the periodic table. So this is hydrogen here going all the way up to uranium up here. And this is how much energy you get out of making things, basically. And this sort of shows you why these reactions work or not. So this is the very first one. This is burning hydrogen to helium. And this is the amount of energy you get. So in sort of arbitrary units, you're getting 7 units of energy out from burning hydrogen to helium. You're jumping a long way up this graph to get energy out. But if you go to burning helium to carbon, you can see it's a much smaller jump. You get much less energy out if you try and burn helium to carbon, but it is still positive, so it's still worth doing. But then as you go further up, here we are burning carbon to oxygen. It's again a much smaller jump. And you can see probably that it gets worse and worse as you go further up the periodic table. It gets less and less energy out from all these subsequent jumps. And by the time you get to somewhere up here, say this would be silicon to iron or something like that, you're hardly getting energy at all out of the reaction. And then here we see iron is the peak. So from here, it's all downwards. You don't get energy out of this. You have to put energy in to get that way. So that's why iron is the limiting factor. But incidentally, you can go this way, which we don't generally see commonly in nature, but it's what nuclear power plants work on, that they can split uranium up into lighter energy elements, and that they're working that way down. Now, how can we see any of these? Luckily, there's processes in the star that from now and again they dredge up these elements. They have a sort of stir around of the things like sort of boiling porridge, and stuff from the innards of the star pops up, and that happens at these various places after the sun goes off the main sequence onto these various other places as it goes into its red giant phase. So that's the first one of making elements. So we can make elements up to iron basically with that process, but no further. But there's a lot of elements beyond iron. So what can we do? Next one is the S process, and this happens in stars that have gone off the main sequence, so they're no longer burning hydrogen into helium, but they're now sort of burning helium into carbon and oxygen. And certain of these reactions tend to give off neutrons. You can see a couple of reactions there. Don't need to know the details, but you can give off neutrons, and neutrons are quite easy to do nuclear reactions with. They're not charged, so you don't get this repulsive force as they come towards. So if they happen to collide, they make a very good process of doing reactions. And this is the sort of star that this will be occurring in, something that is quite close to the end of its life. Still got millions of years of life left, but probably not billions at this point. And this process happens, so you take a random element here, X, and this doesn't stand for hydrogen or anything, it just stands for some random element X. And the S process says you hit it with a neutron, and the neutron comes along and sticks in, and this makes this element very slightly heavier. So the atomic number goes up by 1 because there's now 1 extra particle in the nucleus. So it was, I don't know, pick 16, it would now be 17, but it would still be the same type of element. So if it was 16, which is oxygen, it would now be oxygen 17, but it's still oxygen. But quite often, if you put too many neutrons into the mix, you might think more and more Velcro is good, but it is only up to a point. After a while, it gets sort of uneasy with this amount of neutrons in the core, and it will try and convert one of them back to a proton to try and get a nice balance again. That's a very hand-wavy way of doing quantum mechanics. And anyway, it will turn from a neutron to a proton and kick out an electron to balance the charge, and this will actually bump you up 1 level up the periodic table. So if this was oxygen going from oxygen 16 to oxygen 17, this reaction which kicks out the electron would turn it into nitrogen, is it? I think it's nitrogen. So you can sort of ease your way up the periodic table by this process. But it's called the S process because it's a very slow process. Typically, a neutron like this only comes along once every 1,000 years or so, and will go through this process. And you can work your way up the periodic table. So here we see in this case going from silver all the way up to antimony. So here's silver 109, happens to be just floating around in the outer envelope of the star, hit by a neutron, turns it into what would be silver 110, which would be here. But silver 110 is radioactive, and it decays through this beta decay. In 24 seconds, it goes into this cadmium 110. So it doesn't stay a silver 110 for very long. So it turns into cadmium. Cadmium can actually pick up a number of neutrons, can go through all sorts of stable ones, all the way up to 114. But when it gets to 115, it gets to an unstable form of cadmium with a half-life of 53 hours. But it's waiting about 1,000 years for another neutron to come along, so that never gets to that, and it will decay into indium in this case. But you can see here there is a cadmium 116, which is stable, but it can never get there through this process. It will always decay in this 53-hour process before 1,000 years of another neutron comes along. So you can wander up the periodic table this way and get to certain elements, but some places you just can't get to. So cadmium 116, tin 122, antimony 123, you can't reach any of those by these processes because it decays too quickly. But this produces a certain number of elements by this way. The other one is the R process. So S was for slow process, R is for rapid process. And this happens in supernovas and neutron star mergers. So you get a lot of neutrons flying around in these processes. So this is a supernova predicted here. The star collapses in, stalls for a bit, and then explodes out violently with a lot of neutrons rather, given off. So it's much like the S process. The element absorbs a neutron, then it would normally decay. I mean, it's 53 hours or 24 seconds or whatever. But in this case, there are so many neutrons around that it gets hit by another one, and then another one, and another one, another one, and it shoots up the periodic table very quickly, and then we'll sort of have a quick collapse down. So here we have it. Rather than just one neutron idling along and then waiting, you get hit by lots and lots of neutrons, and you work your way up the periodic table very, very rapidly, and then you probably get several decays in a short time. So you can get to all sorts of places by this process. And this is often shown on this diagram. So this sort of line up here, this is where sort of stable things hang out. This is where nice stable elements are. And if you're on this side of the line, then you're somewhere in the S process, and you're not going to make so many things. So you sort of move up and decay back down to this stable line. There is another process that I thought I'd mention in passing, but nobody's quite sure if it exists. There's both a P and an RP process, where you get lots and lots of protons added quickly to a nucleus. And this perhaps happens in accreting neutron stars, is the only case I've come across. Astronomers think it might happen, but nobody's quite sure. I just thought I'd mention that. But anyway, going back to this diagram, you can sort of get here's the S process working its way up this side, the R process along here. You can get much further off the sort of beaten track into the R process. The S process tends to sort of hug this curve as it goes up, and the black ones are all the stable nuclei. So that's essentially where all the atoms want to end up. We know these things happen because we've detected a few of them now. Particularly neutron star mergers seem to be a very big source of heavy elements. So this was detected by a gravitational wave chirp, and this is an illustration of two neutron stars merging. And as you might guess from the name, neutron stars made lots and lots of neutrons. So when they do merge, you get this big, enormous outpouring of neutrons. So you can make lots and lots of these really big elements very, very quickly in this big explosion. So that was the neutron star merger that happened a few years ago. That was detected, and over 3,500 authors were on the paper that detected that. Anybody near a telescope? I was one of the few people in the astronomical community who wasn't on that paper. There's about 7,000 astronomers probably worldwide, and about half of them were on this paper. So I'm in the other half. And the final way of making things is called spallation, and this is where you break up bigger things and trying to keep with the heavy metal band. So here's a heavy metal on stage, and this is essentially where you throw in something at high speed into the mix, and then you get something else ejected out of it, in this case an osiosperm particle. So less heavy metal bound. This is formed with cosmic rays, which are very high, very fast moving particles going at extreme speeds, some of the most energetic things in the universe. And as they go zooming through the universe, they will occasionally collide with an atom that's floating around doing its own thing, and they will sometimes chip bits off the atom essentially, or fracture it, typically often giving off a helium nuclei. So I said these alpha particles or helium nuclei are very stable, so they tend to come off. So this is a good way of making smaller elements from bigger ones by these high velocity collisions. And this brings us perhaps to our final periodic table, although we're going to revisit this. This shows you where all the elements are thought to have come from. So you can see there hydrogen and helium are from the Big Bang. They're the ones in blue. Yellow come from exploding massive stars. That's the supernovas. Merging neutron stars are all in purple. So you can see a lot of the really big heavy elements are made probably from merging neutron stars. but not in all cases. Cosmic ray fission is the pinkish one, so beryllium and boron and a bit of lithium is all made from this sort of stuff. And where do we go? Dying low mass stars make some of the green ones. So you can sort of just look up, if you've got a particular element, you can see where it comes from. So if you happen to have say a gold wedding ring or something, you can predict where most of that came from. So most of it came from a merging neutron star, with perhaps a tiny bit from a dying low mass star. Whereas if you've got iron, for instance, exploding massive stars and exploding white dwarfs give off lots and lots of iron. So that's kind of where you get those from. Now, just in the last few minutes, hoping some of you are still awake, what can all this tell us? So the first thing it can tell us is about the age of stars. So you can think, if you're going through this process, you're turning hydrogen into helium and then helium into carbon. If you look at a star and you see more carbon in it, it's probably been around longer. And if it's got more of the heavy elements, it's probably been around even longer. So the more metals a star has, the higher its impurities rather than hydrogen and helium, then the younger it tends to be, because it must have got either made it within the star, or more likely it's been made out of a gas cloud floating around in the galaxy with lots of these metals in that have been exploded out from other stars. If you're looking for really old stars, you want to go looking for those which have almost no impurities on. Another way of saying that is big stars with very low metals and very short lives. These would be what we call population 3 stars. These are a type of star we've never seen, but would have occurred very soon after the Big Bang. Because they're very big, they got very short lives, so we wouldn't expect to see many of them around today. But that would be the population 3 stars. Population 2 stars we do see in our own galaxy. They have quite a range of different stars, but all with very reasonably low metals, less than the 2% you see in the sun. And then we have the population 1 stars, which are young stars like our own sun, higher metals than the average, than the population 2, which shows they're more recent, which is one way we work out how old the sun is and how old other stars are. Where do you find these populations? So across the galaxy, population 1 stars tend to be in the spiral arms, which is where we live. Population 2 in the center, and also in the halo of stars are drifting above and below the galactic disk. So that's where those end up. Another useful property is for actually forming stars. So stars form from big clouds of gas, but only when it gets cold enough. So the gas has to get very cold so it will condense down to tiny amounts and then let gravity take over and form the star. And hydrogen on its own is very bad at cooling. You can see this is the cooling curve of hydrogen. So this is increasing temperature across the bottom here. And this is how, up here is how good it is at cooling. So you can see here's the hydrogen. It's pretty good at cooling once it's around about 1,000 degrees. But once you get really hot, it gets very poor at cooling down. So if you've got some really hot hydrogen, it's very bad at getting cold. And this is where some of the metals come in. So if you've got some carbon in the mix, then that's very good at getting rid of this excess energy. So is oxygen, neon and iron. They all have their part to play. So if you have a lot of mixture of these impurities in your gas cloud, then it can cool much more effectively than a pure hydrogen gas cloud. And we'll see where that's useful just in a couple of slides' time. It can also tell us about galaxies. So this is a plot of our own galaxy. So let's find my cursor again. Right, so over here, this is the very center of the galaxy, and this is going outward from the center. So we're about somewhere around here, going out from the center. And this is the amount of metals. So you can see where we are, there's quite a lot of metals. They tend to occur quite a lot around there. So that's a good place to look for rocky planets and other things like that, because there's a lot of that sort of stuff around. It's probably also a good place to look for life that of the sort that we know anyway, carbon-based life forms. Because as you go towards the centre, there's less and less metals over here. As you go to the extreme outer edges of the galaxy, there's less and less stars there, so less and less metals there. Another thing they can tell us is about ages of galaxies. So there are broadly two types of supernovas. There's the core collapse supernova, which was the one I described before, which is where a big star collapses in on itself and then explodes. These are called type 2 supernovas and also type 1b and 1c. And then we also, these core collapse ones, I should say, are very rich in what we call alpha elements. These are even numbered elements. So magnesium, silicon, sulfur, calcium, argon, these are all alpha elements. And you can see this even on the Earth, that these are very popular. So sort of every second element seems to be a lot more common than every odd number element. So the alpha elements, which are built up from alpha particles, tend to sort of be a lot more common. So supernova type 2s, these collapsing core collapse supernovas, they give off a lot of these alpha elements. The other type of supernova, the type 1a, which is an exploding white dwarf, these tend to give off a lot more iron. They do tend to give off some alpha elements, but you get a lot more iron and iron-like elements from a supernova type 1a, of which I have a picture here. So why is that important? Well, what can you gather from this? Well, going through the cycle, big stars, particularly very big stars like Rigel, many times the mass of the Sun, they go through their fuel very quickly because they burn through, so they die very young and they end up with these core collapse supernovas. So very quickly, just in a few million years, they will go through their fuel, die, and give off this big explosion, core collapse supernova, and you'll get a lot of these alpha elements given off in the explosion. So if you just look at, say, even a distant galaxy and you see a lot of alpha elements in it, you know there's been a lot of supernovas happening. And you will only have got these supernova type 2s if you recently had a big population of stars created, or you're continually making stars. So this says something about the age of the galaxy. On the other hand, small stars, they live for a long time. Certainly stars like our own Sun, 10 billion years. Some of them will turn into type 1a supernovas, but only after a long time, only after a number of billion years. So several billion years, they will turn into a type 1a, and they will give off lots of iron in their explosion. So you can sort of see there's two waves. There's after you've created a load of stars, very soon after that you'll get this big explosion of type 2s. Then there's pause, and then there's another sort of wave of type 1a's that come later. So we can measure this with spectroscopy. We can, particularly common is to measure the amount of magnesium. You look for the magnesium line in the spectrum and the iron line, and you look at how much of each of them is present. And if there's a lot of magnesium compared to iron, then this is a galaxy that is making lots of new stars or has very recently made lots of new stars. So it's relatively young and still active. If instead you look at it and you see quite a low concentration of these things, that's because you've got a lot of these type 1a's and they're giving off a lot of iron. So the ratio of magnesium to iron is depressed because you've got a lot more iron. So we know in this case that it hasn't been making stars and it hasn't been doing that for a long time. So you can feed all this sort of stuff in, and this is what some astronomers do sort of all day, every day. They feed it into these stellar synthesis population models, as they're called, and you feed into it all sorts of other things, including how frequently stars are born and all sorts of other things. But there's now computer code to do that, so you just feed in all these spectrums and things. Excuse me. And out comes an age. So it's a rough and ready age, and they're always trying to improve them. But this gives you a quick guess about how old this population is. And that lets us answer a couple of interesting questions. So galactic evolution is one of those that we study at Nottingham. So we have two classes of galaxy. We have those with spiral structures, which are very blue in colour, and we have elliptical galaxies, which are very red. And they form into these two clouds. If you plot them on this, so this is colour up here going from blue to red, and across the bottom is how heavy they are going from low to high. So we know that spiral galaxies start in this blue cloud. This is where they live. They're in the blue part, and they're also quite a lot less heavy than the red ones. But we're fairly sure at least quite a lot of them turn into red galaxies at some point. But we don't know which route they go. They could go this route. They could get bigger and then get redder, or they could go this way and get redder and then bigger. And this is one of the cases where we use some of this aging things. We're trying to look for galaxies that are in this red area of the diagram, but if they've showing still quite high levels of alpha elements, then they have been in the blue cloud more recently. So we look for these sorts of galaxies and then try and work out what's going on there. So that's just one example of how you can use some of this stuff. So I'm going to wrap up now because I spoke at least 10 minutes too long. So sorry about that. But anyway, I thought I'd leave you with this slide showing you all the different elements again and where they come from. And this is quite interesting to ponder on. This is a Wikipedia page, so you can go to the Wikipedia page on elements and metals and find this same graph. So thank you very much for listening. I'm going to put a link in the chat for the Zoom link that if you haven't got it already, I'll put it in there so that you can come and join us over there. But I'm going to end the live stream now and instead switch over to the Zoom link. And if you're not bored of me already, you can ask me some questions there or just chat about general things. So it's going to be a time-limited Zoom because I'm still on the free version. Anyway, I shall see you there. So goodbye, and I hope you found at least bits of this interesting.